Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 129. Water at 20 degrees Celsius of viscosity 0.001 Pascal second is to be pumped through 600 meters of pipe from reservoir A to B as shown below. If the pipe is cast iron with absolute roughness of 0.26 mm of diameter 150 mm and the pump is 75% efficient and delivering 75 horsepower to the flow, what flow rate Q results? So here is the given figure, and for our solution we note that this 75 horsepower is delivered to the flow, so therefore this is already the output power. So when there is a pump installed in the system, the power generated by the pump is output power, and it is equal to weight flow rate Q times specific weight of the flowing fluid or liquid times the head added by the pump. So that's our equation. Power output equals Q gamma head added divided by 0.746, because we want to express the power to horsepower. So again, this is already the output power because this is delivered to the flow, and therefore there's no need to divide it by, we don't need to compute the input power. It's 75 horsepower, that's the output power already. So writing energy equation between point A and point B on the water surfaces on the reservoir. So velocity head, pressure head at A, elevation head plus head added equals velocity head at B, pressure head at B, elevation head at B, then plus head lost from A to B. So our datum is chosen at elevation 0. So in order not to confuse ourselves, so velocity head at A is negligible or 0, pressure head exposed to the atmosphere, so that's 0, elevation head is 50, then head added unknown, velocity head at B is negligible also, pressure head is 0, exposed to the atmosphere, elevation head 86.6, then we have head loss from A to B. So substituting 0 plus 0 plus 50 plus head added equals 0 plus 0 plus 86.6 plus head loss from A to B. Therefore, the head added is uh, 36.6 plus head loss from A to B. The head loss from A to B is equal to friction factor, or 0.0826 friction factor, length discharge square over diameter to the fifth. So power output 75 is weight discharge times specific weight of water, which is 9.81 if not specified in the problem, then head added divided by 0.746 in this equation. Then we can set up Q times head added, which is equal to 5.7034. Likewise, head loss from A to B, or this is the Colebrook equation, 1 over square root of F equals negative 2 log E over 3.7 D plus 2.51 over Reynolds number square root of F. And we must have an expression for F in terms of V, or yes, in terms of V. So Reynolds number, diameter, mean velocity, density over viscosity. So diameter 0.15, mean velocity we do not know V, density of water 1000 over viscosity 0.001. So the Reynolds number is equal to 150,000 V. Then the head loss from A to B is equal to, this is the Reynolds number, by the way, in terms of the discharge, where V is 4 times Q over pi diameter square. So it is 8488264 of Q. Then head loss from A to B is equal to 0.0826 friction factor, length 600, discharge square over diameter 0.15 to the fifth. So that head loss from A to B is equal to 65264 F Q square. So in this equation, we should set value of F so that we can compute Q in this equation here. Head added is 5.7034 divided by Q. So 5.7034 over Q equals 36.6 plus head loss, which is 65642 FQ square. So if we set value of F, then we can compute Q, and we make sure that the left side of the equation in the school book equation should be equal to the right side of the equation. So we have to try values of F until such time that the left side of the school book equation is equal to the right side of the school book equation. So one good value is, the common value is 0.02. So 1 over F, square root of F equals negative 2 log 0.26 over 3.7 times 150 mm plus 2.51 over Reynolds number 8488264Q, then square root of F. So again, we set value of F 0.02. Then in this equation here, we estimate Q in this equation. So if F is 0.02, substitute into this equation, we can compute Q 0.06369 cubic meter per second. Then let's check if the left side of the school book equation is equal to the right side. The left side of the equation is 1 over square root of 0.02. And the right side is negative 2 log of 0.26 over 3.7 times 150 plus 2.51 over 8488264 Q. Q is 0.06369. Then square root of 0.02. So the left side is 7.071, which is greater than the value at the right side, which is 6.600. So we must increase a little F, then the right side will also, if we increase F, then the left side will decrease a little, then the right side will increase a little until they meet or until they are equal. So finally, when F is 0.02294, then Q is 0.06135 cubic meter per second. Substitute into this equation. So 1 over square root of 0.02294. So we have to compare it with the value of the right side. So we just substitute the value of Q. So we copy, then substitute the value of Q, which is 0.06135, then F 0.02294. The value of F, the value of the left side is now equal to the value of the right side. So therefore, because they are equal, therefore the discharge is 0.06135 cubic meter per second. And that's our answer. Problem 130, oil of specific gravity 0.9 and with kinematic viscosity of 0.00065 square meter per second flows in a 75 millimeter diameter pipe at the rate of 10 liters per second. So compute part A, the head loss in a length of pipe of 300 meters, the maximum shear stress, and the velocity at the point 10 mm from the center line of pipe. So let's check the type of flow by computing the Reynolds number. So we can compute the velocity, mean velocity of flow, because the discharge is given, and we are also given the kinematic viscosity as well as the specific gravity of oil. Head loss, by the way, is friction factor length over diameter times velocity head. So the velocity can be computed. It is only the friction factor that is required here, that is needed. So let's check the type of flow by first computing the velocity. So this is the Darcy-Weisbach formula for head loss. Then we need F here. So velocity is 4 times discharge, 0.01 over pi times 0.075 meter quantity square, and it is 2.2635 meters per second. We then compute the Reynolds number, which is diameter, mean velocity of flow, divided by kinematic viscosity. Diameter, mean velocity of flow, divided by kinematic viscosity. So Reynolds number is diameter 0.075, mean velocity of flow 2.2635 over kinematic viscosity 0.00065. So the Reynolds number is equal to 261, which is less than 200, and therefore the flow is laminar. The friction factor for laminar flow is 64 divided by 261. So we substitute it into this equation here. Length is 300, diameter is 0.075. So we can now compute the head loss in the length of 300 meters. So friction factor is 64 over 261. So we substitute it into this formula. So head loss friction due to friction is 64 over 261, length 300 over diameter 0.075, velocity head 2.2635 square over 19.62. So the head loss is equal to 256.1 meter. Then for part B, the maximum shear stress, it is equal to tau sub O, and it is equal to specific weight, head loss, diameter over 4L, and the other formula is friction factor, density, velocity square over 8. So tau sub O is friction factor, density, velocity square over 8. The other formula is specific weight of oil times head loss, which is already computed, times diameter over 4L. But we will just use this anyway in our previous examples similar to this. Both formulas will yield the same answers or results. So friction factor is 64 over 261, density is 900 kilogram per cubic meter, 0.9 times 1000, specific weight of water 1000, density of water 1000. So specific gravity of oil times 1000 is 900 kilograms per cubic meter. Velocity already computed. So tau sub O is friction factor 64 over 261, density 900 times velocity square 2.2635 square over 8. So the maximum shear stress is 141.3 pascals. Then for the last question, part C, the velocity at the point 10 mm from the center line of pipe, since the flow is laminar, V sub R is V sub C, where V sub C is 2 times the mean velocity of flow times the quantity 1 minus R square over RO square, where R is 10 mm and R sub O is the radius of the pipe, which is 37.5 mm. So substitute V sub R equals V sub C, quantity 1 minus R square over RO square, and V sub C is 2 times the mean velocity of flow. So 2 times 2.2635, quantity 1 minus 10 square over 37.5 square. So the velocity there is 4.205 meters per second. Problem 131, gasoline with a kinematic viscosity of 5 times 10 to the negative 7 square meter per second flows in a 300 millimeter diameter pipe. Find the flow rate in liters per second when part A, the head loss is 0.6 meter per 100 meters and the pipe is smooth. B, the head loss is 12 meters per 150 meters and the pipe is fully rough with absolute roughness of 3 mm. And part C, the head loss is 4.5 meters per 200 meters and pipe is cast iron with absolute roughness of 0.26 mm. For our solution, so let's have the formula by Darcy Weisbach. So we need friction factor here. For part A, the pipe is smooth. So Colebrook equation for smooth pipe is 1 over square root of F equals 2 times log quantity R sub E, Reynolds number square root of F divided by 2.51. Then we set up dead loss by Darcy Weisbach formula, which is FL over D times velocity head. So HF equals FL over D velocity head, and head loss is zero point 0.6, so F times 100 over diameter 0.3 velocity head. Then we can set up formula for FV square. So FV square equals 0.035316. Then by Coolbrook, Reynolds number is diameter mean velocity of flow over kinematic viscosity. The diameter is zero point 0.3, mean velocity of flow we do not know. Then velocity, kinematic viscosity is 5 times 10 to the negative 7 square meter per second for gasoline. So it is equal to 0.3 mean velocity of flow divided by 5 times 10 to the negative 7. So the Reynolds number is 600,000 times V. Then into Colebrook's equation, 1 over square root of F equals 2 log times quantity R sub E square root of F over 2.51. Where square root of F is from this equation, square root of 0.035316 over square root of V square, which is V. So square root of F is 0.18793 over V. So we substitute it here. So 1 over square root of F becomes V over 0.18793 equals 2 log of quantity Reynolds number 600,000 V. Then square root of F is 0.18793 over V. So we can cancel V here. So we can evaluate this value, then multiplied by 0.18793. So we can now compute for the mean velocity of flow. So the mean velocity of flow is 1.7487 meters per second. So the flow rate in liters per second can now be computed. So pi over 4 times 0.3 squared times 1.7487 times 1000. So the flow rate or the discharge is 123.6 liters per second. In the second part, the head loss is 12 meters per 150 meters and pipe is fully rough with absolute roughness of 3 mm. So Colebrook's equation for pipes behaving as fully rough is 1 over square root of F equals 2 times log of quantity 3.7 over E over D. So 1 over square root of F equals 2 log of quantity 3.7 over E over D. So everything is known. So we can solve for F. So 1 over square root of F equals 2 log of quantity 3.7 over 0.26 sorry, over E 3 over diameter 300 mm. So friction factor is equal to 0.037904. Then substitute into Darcy-Weisbach formula. Head loss 12 equals friction factor 0.037904. Length is 150 over diameter 0.3 times velocity head. So the velocity is mean velocity of flow is 3.5346 meters per second for this case. So the discharge can now be computed, or the flow rate, pi over 4 times 0.3 square times 3.5346 times 1000. So the flow rate is equal to 249.8 liters per second. Then finally, for the discharge when the head loss is 4.5 meters per 200 meters and pipe is cast iron with absolute roughness of 0.26 mm. So this is the situation where we have transition from smooth to fully rough pipe. So we use Colebrook equation 1 over square root of F equals negative. This is the head loss 4.5, friction factor length 200 over diameter 0.3 velocity head. So we can set up FV square, which is equal to 0.13244. So square root of F is square root of 0.13244 over V. Then that would be 0.36392 over V. Then Colebrook's equation for transitional case, transition from smooth to fully rough, is 1 over square root of f, or V over 0.36392 negative 2 log of E over 3.7 D plus 2.51 over Reynolds number square root of f. So again, the formula by Colebrook is 1 over square root of f. So 1 over this value, so it becomes V over 0.3692 equals negative 2 log of the quantity absolute roughness E over 3.7 D plus 2.51 over Reynolds number square root of f. So it is a combination of this smooth pipe formula and this fully rough pipe by Colebrook equation, because a negative sign is preceded here, so we have to invert this formula here. So this is also inverted. That's why we have E over 3.7D here. So we can cancel V. We can actually evaluate this right side value, then times 0.36392. Then we can compute for the mean velocity of flow, which is equal to 2.6272 meters per second. Then the discharge, pi over 4 times 0.3 squared times 2.6272 times 1000. So the discharge is equal to 185.7 liters per second.